电压钳技术带来的最显著的成就是Hodgkin 和 Huxley 对动作电位的定量描述 Hodgkin Huxley 模型，或称 Hodgkin Huxley 方程。由于涉及到常微分方程或偏微分方程，该模型一般被排除在很多教科书之外。然而，现代科学需要多学科的整合， Hodgkin 和 Huxley 的工作就是这方面最佳范例。这就是为什么我想花一些时间研究 Hodgkin Huxley 模型的原因。此外，我想说明 Hodgkin Huxley 方程并没有大多数人认为的那么难。
The most remarkable achievement as a result of the voltage clamp technique is the quantitative description of the action potential, the Hodgkin Huxley model, or the Hodgkin Huxley equations. This model is generally excluded in textbooks because it involves ordinary or partial differential equations. However, modern science requires integration of multiple disciplines, and the work of Hodgkin and Huxley is the best example of this. This is the reason why I want to spend some time on the work by Hodgkin and Huxley. Furthermore, I want to show that the Hodgkin-Huxley equations are not as hard as most people think.
PyHH was developed by me using Python. It is a small library for building compartmental HH models simulating neuronal activities. Before we touch on the theory of the HH model, I am going to go through some code examples to show what the library offers.
PyHH 是我使用 Python 开发的用于构建 HH 模型的小型库。HH 模型是 Hodgkin 和 Huxley 在1952年提出的，用以定量解释神经元的电活动。在我们接触 HH 模型之前，我将通过一些代码实例来展示 PyHH 到底能做什么。最初开发这个文库的目的是想帮助电生理新手理解膜片钳和生物电的基本原理，所以把它放到 GitHub 上。不过，这个文库没有得到过关注，我也忘记了我的 GitHub 账号密码，直到最近发现了密码，所以打算把这个文库介绍给各位。
The original purpose of developing this library was to help electrophysiology novices understand the basic principles of patch clamp and bioelectricity, so I uploaded it on GitHub. However, this library has not received any attention, and I forgot my GitHub account password. Recently I found the password, so I made some modifications to the library, and I plan to introduce this library to you.
This is my GitHub page for PyHH. The URL. There is a green button. Click it. A dialog window popped up. Click the download zip button. You can unzip the file and put the folder wherever you want.
在讲解 PyHH 的使用方法之前，我先展示几张 PyHH 生成的图片。
I will explain how to use the PyHH library. But first, I am going to show a few pictures generated by PyHH.
这个图显示了神经元的阈值行为。在弱电流刺激下，神经元膜就像一个与恒定电容器并联的恒定电阻器。但是，当去极化足够强时，神经元会激发动作电位。
This shows the threshold behavior of the neuron. With weak current stimulations, the neuron membrane acts like a constant resistor in parallel with a capacitor. But when the depolarization is strong enough, the neuron fires action potentials.
在 PyHH 中，细胞体被模拟成一个球体，树突或轴突被分成相互连接的圆柱体，称为格式。在这个例子中，神经元有一个直径为40微米的细胞体，胞体附有3个突起，直径均匀，为3、2和1微米。每个突起长300微米，分为15段，图中仅显示3段。
In PyHH, the cell body is modeled as a sphere. The dendrite or axon is divided into linked cylinders, called compartments. In this example, the neuron has a cell body with a diameter of 40 micrometers. 3 processes are attached to the cell body, with uniform diameters of 3, 2, and 1 micrometers. Each process is 300 micrometers long and divided into 15 segments.
我们给细胞体一个电流脉冲，诱发动作电位。动作电位沿3个突起传播。可以看到，动作电位的传播速度与直径正相关。
We apply a current pulse to the cell body, which causes an action potential. The action potential propagates along the processes. It can be seen that the propagation speed of the action potential is positively correlated with the diameter of each process.
这个图显示的是电压钳实验结果，细胞膜电位被钳制在不同水平，然后记录钠离子流。
This figure shows the results of a voltage clamp experiment in which the cell membrane potential was clamped at different levels, and then the sodium ion current was recorded.
要使用 PyHH， 您需要安装 Python。好消息是 Python 并不难安装。此外，您不会后悔安装它。
To use PyHH, you need to install Python. The good news is that Python is not hard to install. In addition, you are not going to regret installing it. I haven't used Windows for more than 20 years. I use Ubuntu, which comes with Python pre-installed. If you are using Windows, you have to install Python yourself. I did have experience with Python on Windows, but that was 20 years ago. It seems it is not hard to install Python on Windows.
我已经20多年没有使用 Windows 了。我确实有过在 Windows 上使用 Python 的经验，但那是20年前的事了。我使用 Ubuntu 预装了 Python。如果您使用的是 Windows， 则必须自己安装 Python。在 Windows 上安装 Python 似乎并不难。
To install Python on Windows, go to the official Python download page for Windows. This is the web page where you find the right file to download. Select the Windows installer. After the installer is downloaded, double-click the .exe file. Click Install Now for a simpler installation process. Make sure to check the following checkboxes. Use admin privileges when installing py.exe. Add python.exe for the path checkbox. Verify whether the Python installation is successful. Go to Start and enter CMD in the search bar. Click Command Prompt. Enter the following command in the command prompt. Python version. An example of the output is output Python 3.11.4. Let's see the first example. This script shows how to create a basic HH model using predefined sodium, potassium, and chloride channels. Since there is no current stimulation, we can only see the resting potential. If you are working on Windows, you need to start the command line and navigate to the folder which contains the PyHH files you have downloaded from GitHub. One way to change directories in the command prompt is to type a CD followed by a space, drag and drop the folder you want to browse into the window, and then press Enter. Step 1. Import compartment, experiment, and 3 predefined channels. Step 2. Define channel densities and reversal potentials. Step 3. Define a cell and add channels to the cell. Step 4. Define an experiment instance for equation integration. Step 5. Run the integration. Step 6. Plot the result. The first step is to load what we need into the memory. The compartment for defining the neuronal geometry. The experiment for solving the equations. And predefined sodium, potassium, and chloride channel classes. We define a dictionary describing the conductance densities and reversal potentials. Actually, the dictionary can be written in one line. In step 3, we use 2 statements to define a cell. But they combine into an equivalent form. Step 4 defines an experiment on the cell we just defined. In step 5, we run the experiment, and finally, in step 6, we plot the membrane potential. Let's do it. I use Ubuntu. I start a terminal, and cd into PyHH folder. Launch the Python interpreter by typing Python. Now you know what to do. Oops. Okay, this is the resting potential. There is nothing fancy about it. If we just type 3 extra lines of code, we can get a beautiful action potential. Clamper stands for current clamper. Here we define a clamper, and at the same time, we clamp the cell we just used for generating the resting potential. We need to set the waveform of the stimulus. We use a rectangular pulse. Finally, we repeat the previous statements to generate the action potential. Let's do it. This is the current pulse. This is the action potential. You can see the artifact. Close the figure window. Quit the Python environment. Next time, I am going to show more PyHH examples, and then dive into the details of the Hodgkin Huxley model. I will talk about what we learn from the history of electrophysiology.